Question 7. The bubonic plague. In the late Middle Ages, Europe experienced the most deadly disease outbreak in history. The Black Death, the infamous pandemic of the bubonic plague, hit in 1347, killing about a third of the European population. The table Plague stores information about a random sample of 750 citizens in a neighborhood of London in 1349. The first few rows are shown here. The table is 5 columns. Survived is 1 if they survived, and 0 if they died. Street is the street where they lived. Sex is male or female. Age is the age of the person. And then income is how many thousands of pounds their income was per year. So suppose we want to test whether or not there's a difference between the distributions in street between those who survived and those who died. So what test statistic would be the most appropriate for this question? So we're given a few examples of streets here, like Oxford and Holborn and Bedford, and we want to know, do the different streets have a different rate of survival and non-survival, I guess. So the key thing here is that street is a categorical variable, and there are a bunch of different streets that you could have lived on. So for a categorical variable where there are multiple different categories, that lends itself to using the total variation distance as a test statistic. Okay. The plague affected some parts of Europe more than others, and historians disagree over the exact number and the exact proportion of deaths in each location. We'll assume the typical death rate is 33%, that 33% of people in cities died from the Black Death. However, in a sample from this particular neighborhood, 40% of people died. In parts B through D, we'll use a hypothesis test to examine the claim that this neighborhood had an unusually high number of people who died compared to the typical rate of 33%. So part B. Which of the following are correct choices for a null hypothesis? Choose all that apply. So this first one, exactly 33% died, that's not true because of the word exactly. So remember that the null should give a model under which we can simulate, and saying exactly 33% died is not an example of that. Okay. Each person in the sample had a 40% chance of dying, independent of every other person. So this is also not it, because under the null, we're assuming there's no difference between normal cities and this one. So 40% would be an alternative hypothesis, not a null. Third one, each person in the sample has a 33% chance of dying, independent of every other person. So this is correct, because it gives an accurate model, which is 33% chance of dying, and because it tells us it's independent, that tells us how to simulate this null hypothesis. Okay, the next one is that each person is equally likely to survive or die, independent of every other person. That's not true, because equally likely means 50%, but we know that the death rate was not 50%. Okay. Fifth one. The distribution on which street people lived on is the same as between people who survived and people who died. Any difference is due to chance. So this one looks very plausible because it tells us that it's comparing the distribution of which streets people were on. However, this is not a correct null hypothesis because it does not give us a model to simulate under. So we need to know exactly how likely it is that someone will die under this null. Okay, the last one is that male and female citizens died at equal rates. So this is not a good null hypothesis because it's not testing what we want to test. We're testing this city versus, or this neighborhood versus others. We are not testing male versus female. Okay, part C. For our test statistic, we choose the number or the percentage of people who died. Which of the following Python expressions will definitely not appear in our code to simulate? Choose all that apply. Okay. So sample proportions, this is possible because if we take, it's plausible that we can make code that's like def model is make array of 0.33, which is the chance of dying, and 0.67, which is the chance of surviving. And then we can take death proportions equals sample proportions and then we can call this on a sample size, so we can say 100 people, and then using death model. And that would tell us how many or what proportion of these 100 died. So that is possible to use sample proportions. Okay. This second one says plague.sample with replacement is false, and we would not do that because when we sample with replacement false, that generally means we're shuffling labels as we would in an A/B test. However, this is not an A/B test. This is just a standard hypothesis test. Okay. The third option is plague.join. So what join does is it can take two tables that have one column in common, and then it'll make a new table that combines the data from both of them. And we would not be able to use that because we only have one table here. So there's really nothing to join it with. And even in past hypothesis tests, we've never really had a use for the join function. Okay, so the next one is plague.group. And I would say, yeah, that is possible to use. So for example, we can get, let's see. One example where we can use this is we can do plague.group by survived. And what that'll do is it'll give a new table with the data among everyone who did not survive, and then the data of everyone who did survive. So it is definitely possible to use group in this situation. So the last one is np.append, and this one is also possible to use. In any example of a simulation, we will definitely use np.append. So for example, stats equals make array for I in np.arrange of 1,000. So we're repeating this simulation 1,000 times. We can say stat equals 1 stat, which is just an example function that will compute one value of the test statistic, and then we can say stats equals np.append stats stat. So we definitely will use np.append. So our answer is plague.sample with replacement equals false and plague.join. Okay, D. For this part, assume that our simulation gives each person a 33% chance of dying, regardless of your answer to part B. So, suppose we simulate this neighborhood's deaths under the null 10,000 times and record our test statistic for each simulation. We compare our observed test statistic of 40% to the observed test statistics and find that our p-value is 0.06. If the cutoff is 0.05, which of the following are valid conclusions from the test? Okay, so if the null were true and we obtained many random samples, about 95% would give us a statistic of exactly 33%. The keyword here is exactly, and that's what makes this an invalid conclusion. If the null were true, then we would have a distribution centered around 33%, but that does not mean that 95% of the samples are going to be 33 as a test statistic. The second one says, if the null were true and we obtained many random samples, about 6% of samples would give us a test statistic of exactly 40. So this one is also false. This 6% comes from the p-value, but this is an incorrect application of the p-value. we don't know anything about like how many samples would give what test statistic because it's a random process. The third option says if the null were true and we obtained many random samples, about 6% of the samples would give us a test statistic of 40% or higher. So this one is actually a valid conclusion. And here's why. So this is a correct application of our p-value, which is 6%. So let's say we draw a bell curve. So we know it's centered around 33%, right? So 0.33 here. But here we have about 0.40. And we know that the p-value is the percentage of observed statistics or of simulated statistics that are more extreme than your observed statistic. So our observed is 40%, right? And that means that if the p-value is 0.06, then 6% of samples are going to be more extreme than that, aka higher. Okay, so the fourth and fifth options are the probability of the null hypothesis being true is 6% and 5%. Both of these are false because, remember, our null is either true or not true. There is absolutely no probability associated with it. So even though our p-value is 6%, this is not a correct application because if it's 6%, then and our cutoff is 5%, we know for a fact that the null is, we will not reject the null in this scenario. The last one is that the data are more consistent with the null, and that's true by definition. Our p-value is higher than the cutoff, meaning that we should accept the null hypothesis. Okay, so the sex and age columns are important predictors of survival because higher income citizens had better access to nutrition, and men were more likely than women to be merchants on ships that brought the plague to Europe. Fill in the blank with the code to produce the table below, which gives the average household incomes of male and females who died and survived. For example, among female citizens who survived, the average household income was £57,000. Okay, so here we have a pretty different table than what we originally had in plague. Here we have 3 columns, survived, male, and female, and then our 2 rows are did not survive and did survive. So the function we're going to use here is pivot. So we're going to pivot this table, and pivot can take either 2 arguments or 4 arguments. If it takes in 2 arguments, it'll take in the, so pivot, it'll take in the what you want on the what you want the column labels to be. So in this case, we want them to be female and male. So we can do pivot column labels, comma row labels. So that would be survived in this case. But then we have these numbers here, the 42, 57, 45.9, etc. And those are the people's income values. So in this case, we need to use a special version of pivot that uses 4 arguments. So it's pivot of column labels, row labels, comma, and then we have the third and fourth columns, which are what column that you want to have the values. So values, and then you need a function that will collect those values and process them. So collect, let's call it that. So here, we want our column labels first. So we want sex here. Then the second one, we want our row labels. So we would get that by survived. Then the column of the table that we can get our numbers in the table from is income, right? Because it says we want the average household incomes. So we can go income here, And then lastly, we need a function to collect the data. And here, since it has average household income, we want to do np.mean or np.average. So that would give us the answer here. Okay, part F. The histograms below show the age distributions of citizens who survived and citizens who died. Both plots were created using bins equals np.arrange 0, 61, 5. So bins of 5 years each, and they go from 0 years old to 60 years old. So the question is, which of the following statements can we justify based on what we see in the above charts? Select all that apply. So first, citizens with a higher income had a higher chance of surviving. So while this is probably true, that is not apparent from the plots. All we see is the ages, which has no correlation to income. So this is not true. The second is that approximately 1% of the citizens who died were between the ages of 5 and 9. So we can go to the non-survivor table and look at this bin right here from age 5 to 9. So the area of our histogram is the width, which is 5 years, multiplied by the height, which is about 1%. So 5 times 1 is about 5%. So no, this is not true. The percentage of the citizens between the age of 5 and 9 who died is more than 1%. Okay. Third, among the citizens between the ages of 45 and 49, more survived than died. Okay, so 45 and 49 are this bin here and this bin here. So, okay, so here we see the bin is about 4 or 5% high in the survivor graph, and then it is about 0.5% high in the non-survivor graph. So directly comparing the height of the bars actually would not work because there's a different number of survivors and non-survivors. So saying like a higher percentage of survivors or a higher percentage of these people were in the survivors table than in the non-survivors table is not accurate because we don't know exactly how many people survived and died. But in this case, we know that 40% of people in this place died and 60% survived. So we have 60% of all the data is here, and then 40% of all the data is here. So in this case, we do know that 60% of a pretty big fraction of people is larger than 40% of a much smaller fraction of people. So we can say that more people survived than died between the ages of 45 and 49. Next, among the citizens who survived, between 10 and 15% were between 20 and 24 years old. So we can look at the survivor table and look at the bin from 20 to 24. And again, remember the area of the histogram is the width times the height. So it's about 5 years times 1% is about 5%. So 5% is much less than between 10 and 15. So this is false. Okay, next is that all the citizens between the age of 10 and 14 died. And this one is true. If we look at the survivor table, we see literally no one here. There's just not a bar because there are 0 people there, which means that every single person in the town who was between age 10 and 14 is in the non-survivor graph. Then the last one, all the citizens between the age of 25 and 29 died. This is not true. If we look at the 25 to 29 graph or bar here, you can see there are clearly people who did survive. So this is just false. Okay. For parts G and H, use the following scatter plot, which contains 1 point for each female citizen who lived on Holborn Street. The plot shows the age and income for each citizen, with survived represented by the shape of the point. The X's correspond to citizens who died, and the circles correspond to citizens who survived. Suppose we train a k-nearest neighbor classifier to predict whether a given female citizen on Holborn Street survived, given her age and household income. We will use our classifier to predict what will happen to a hypothetical 25-year-old woman whose household income was £25,000 or £65,000, and that's this triangle right here. So G is, if we use a 3 nearest neighbor classifier, what will be the prediction for the woman marked by the triangle? So let's find the 3 nearest neighbors. I would say it's this one right here, this one right here, and this one right here. So 2 have survived and 1 have died. So the most common label is going to be survived. So we will say survive. Okay. Now, part H. If we use a 13 nearest neighbor classifier, what will we predict for the same woman? So now we have to count more. So we got to count. We have 3 already. We want to get to 13. So 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So these are the 13 nearest neighbors. And let's count up the survived versus died. Let's see. I count died 7 and survived 6. So from here, I would conclude that the most common label is died. So we will say, according to a 13 nearest neighbor classifier, she will die.